Hello, everybody. Welcome back to class. You survived the exam. We all survived it. Ugh, what a disaster. Yeah, all right. Let me know in the chat who's here. Oh, the numbers are free falling right now. We are at 8. We're down to 3. Oh no. Isabella, welcome back to class. Hello, Turner. Good to see you. Last semester, on the day after test 2, I had 3 students in one of my classes. It also happened to be a Friday morning, and it was the day after Halloween, but nobody came. Jared, Jax, good to see you all here. We'll start up in a minute or so. Let everybody get to class on time. Akil, what's up? Hello, Ellie. Good to see you. All right, well, it's 10 o'clock. You know what that means? It means it's time for the last simultaneous sip of the week. But it could be the best simultaneous sip of the week. So if anybody would like to join in on the simultaneous sip, I'm going to do it nice and slowly because I see that there's still some people trickling in. Do so now. All right. Well, we survived. Okay, test 2. I haven't looked at them yet. I glanced at them, but I haven't graded anything yet. Sippity sip sippity. Sorry if there's any stress with the PDF uploading thing. We're all trying to figure out how Canvas works. So there's no punishments for anybody that sent it in at 11:01. There's nothing to worry about. We're just trying to iron out the kinks. The other math teachers are having the same problems I'm having. I think it went relatively smoothly though, right? With the other assignment thing. I don't know. So yeah, TA and I are gonna work this weekend to hopefully get these graded for Tuesday. Okay, let me see in the chat. Did anybody click the link that said test 2 solutions? Do not click. I just want to see if you did or not, and then we can actually get started with some math. Akil is an honest man. He said nope. It's okay if people did, because it was a prank, obviously. Ellie said yeah. Nope. I did after I submitted. Yeah, if you haven't yet, you should click it. It was just a joke. I don't want to spoil it for you, but I thought it was. I need to entertain myself somehow, so pranking you all during a test is how I do it. I enjoyed the Rickroll. I wasn't sure if I don't really know how. I mean, I'm not that much older than you all, but I like in terms of memes, the Rickroll is like 10 years old, so I wasn't sure if any of you would even understand that or not. But I'm glad you did. Okay, so we're gonna do 3.7, and feel free to just keep doing whatever you want in the chat. It's Friday. Optimization problems. So this is going to be another word problem section. Okay, so again, we're going to have a little bit of buildup, and then we're going to just probably crank out examples for the rest of the class today, and then on Tuesday as well. So we'll just do a little bit of buildup to start, and then we'll just kind of learn through example. It's kind of the best way to do it with these types of problems. Okay, so optimization problems. We're going to be taking our find absolute max, absolute min type problems, and we're going to just apply them to real world examples. So the methods we have learned in chapter 3 for finding extreme values have practical applications. You should have had the test 2 solutions link to your video to increase viewership. Jared, now that is marketing. That's a marketing strategy that I just cannot, I'm not smart enough to think of that. So that's a great idea. For finding extreme values, okay, sorry. The methods we have learned in chapter 3 for finding extreme values have practical applications in many areas of life. And so in this section, we're going to look at some of these examples. So the types of problems we might look at are maybe we'll want to maximize area. Or volumes. And profits. Or we might want to minimize something else like cost or distance or the amount of time we spend. Okay, so these are the types of problems we're going to look at. We want to either maximize something or minimize something. And luckily for us is we have a whole chapter of techniques to use that tell us how to find the maximum values or the minimum values, right? We have the first derivative test or the second derivative test tells us how to find these extreme values. And so basically we're going to take those tools and apply them to some word problems. Okay, so that's all the buildup, just basically what we're going to be doing. Let's take a look at an example. And this problem is there's quite a bit of writing to it, but we'll make it work. So example. So a farmer has 2,400 feet of fencing. and wants to fence off a rectangular field. That borders a straight river. Okay, and we'll sketch a picture of this in a second, but there's some more. He needs no fencing along the river, right? That's a natural boundary. And so the question is, what are the dimensions of the field that maximize area? Or that, sorry, let's. That has the largest area. All right, so this is the question. So typically with these optimization questions, it's best to start by drawing a picture just so we could visualize what we're dealing with. Okay, so I'm going to draw the picture just so we could have a sense of what's happening here. And then maybe I'll ask for some help in the chat for how to continue the question. Okay, so we have a rectangular field. That borders a river. So we'll say maybe down here is the river. We just got a fish in it. I don't know. He needs no fence along the river, but he needs fence everywhere else. Okay, and so what we want to do is we want to find the dimensions of the field that gives us the largest area, maximizes our area. Okay, so maybe we could call this the length or the width, and we could call this the length. Right, and we want to find W and L that gives us the largest area inside of here. Okay, so are there any constraints in this question that we haven't considered yet? So I guess the question is, what do we want to do? So our goal is to maximize the area. And our constraint is something. So what constraints are there in this problem that we haven't considered? And if you're unsure, just, I don't know, just post a question mark, or let's see if there's any good emojis in here. Do the dab emoji. Yeah, so 2,400 feet we have to consider. And that has something to do with the perimeter, right? All right, I got to stop pressing those buttons. I think I'm going to break the stream. So this has to do with the perimeter. We have 2,400 feet of fencing. So our fencing, the amount of fencing, well, we have W amount of fencing here. We have L amount of fencing here. And we have an additional W here. And we need that to equal 2,400. Okay? And so we want to maximize area. What is the area of our region? And if you're unsure, can you just let me know, is this stream like extra glitchy today? A equals length times width. Yeah, so we want to maximize A equals L W. So the way we'll do that is we'll take our constraint equation. We'll solve. Okay, sure. This is an equation that has 1, 2, 3 variables. We don't know how to maximize, and it has 2 on the right hand side. We don't know. Okay, Giannis says it's smooth. It's smooth enough at least. We don't know how to maximize or minimize functions of 2 variables. Okay, that's something you'll learn in Calc 3. And it's a little bit, I mean, it's not that hard, but there's some tricks to it. Okay, we only know how to optimize or maximize or minimize functions of 1 variable. Here we have 2 variables. So we have to eliminate a variable before we're allowed to use our techniques. And so what we'll do is we'll solve for one of the variables here and then substitute it in to our area function, and then we could try to maximize the area function like that. Jonathan says it's a little bit choppy. Yeah, I should not have tried to do anything with the chat. Hopefully it recovers. Okay, so our constraint is L plus 2W equals 2,400. We could solve for either one of these variables. I think it's easier in this case to solve for L. And now our area is equal to, well, L is 2,400 minus 2W. We can factor this W through. And we have that the area is equal to 2,400W minus 2W squared. And we want to maximize this. We want to maximize this area function. How do we maximize? How do we find the maximum value of a function? Find the critical points. Yeah, exactly. So we want to find the critical points here, which, Isabella, you're right also. Take the derivative. We want to find when our derivative is 0 or undefined. In this case, it's just going to be when it's 0. And then yeah, we want to figure out which one of these gives us the highest value. So the derivative, and the reason why I multiplied the W through, it's not necessary. The reason why I did it was just so we didn't have to do the product rule. it's easier to just do the power rule a couple of times. Okay, so we take the derivative and we get 2400 minus 4w. And so what do we do with this? We want to set it equal to 0 and solve. 600. Okay, so we got w. And now how do we get, right, we want the dimensions. We need both width and length. How do we get the length? Yeah, we'll plug into our constraint equation, which we manipulated to have L equals 2400 minus 2W. So let's use this. So we get L equals 1200. And so our answer is W equals 600, L equals 1200. All right, so are there any questions about this first problem, or can we look at another one? These are, I mean, the hard part about these problems is drawing the picture and then figuring out what we want to maximize or minimize and what our constraints are. Once we do that, then it's just simply a find the absolute max type of question. I mean, technically, we should consider the boundaries, which is when W. I mean, what could happen? You could have no length, but then you'd have no area, and you could have no width. You would also have no area. So the boundary conditions we don't really have to consider because they would correspond to 0 area. But if we're good with this, we could move on to the next example. And again, feel free to interrupt me with the chat with any questions you may have, because typically this is historically this is one of the sections that students are afraid of, but I think it's because it's word problems. It's kind of like people were afraid of related rates when they really they're not that bad. Okay. So a cylindrical can is made to hold 1 liter of oil. Okay, and now I'm going to warn you. We're going to need to do some conversions here. So if anybody that's familiar, if anybody is taking a number of science classes or grew up in a place where they use the metric system, it's your time to shine, because we're going to have to convert liters into cubic centimeters at some point. So it's your time to shine. So we have 1 liter of oil. Find the dimensions that will minimize the cost of the metal used to manufacture the can. Okay, so we have a can. That we want to hold that holds 1 liter. Pretty good drawing, I would say. Okay, so what bits of information, like what are we trying to? We want to minimize something. What are we trying to minimize here? Yeah, we want to minimize the cost, but we don't have. We could assume that the metal is has a fixed cost, has a fixed cost per square centimeter. Yeah, so we want to find the dimensions of the cylinder. Yeah, so what dimensions, like what's our equation that we're going to try to use to minimize? What property are we looking for? Are we looking for its volume? Are we looking for its surface area? Are we looking for something else? Yeah, so we want to minimize the surface area. And our constraint is what? Our constraint, so okay, surface area will be in in square centimeters. Our constraint is that our volume is equal to 1 liter. So my question for you all, how many cubic centimeters are in 1 liter? And this is something I would provide to you if this was on a test or a quiz. But I'm just interested to know if anybody knows the conversion between liters and cubic centimeters. Yes, Jax, there are 1,000 cubic centimeters. Okay, so we have this constraint that our volume has to be 1,000. And we want to minimize surface area. Okay, so let's draw this picture again, just so we could give it some name. Name some variables. The can has some sort of height and some sort of radius. Yeah, so it seems like a few of us knew the conversion. I did not know. That's why I asked. Ignorant American not knowing the metric system. What is the volume of a circular cylinder? What is the volume of a cylinder in terms of its radius and its height? Well, it's just the area of the circle times the height. So that's pi r squared h is equal to 1,000. Okay, so this is the volume of a cylinder, and it has to be 1,000. Ah, good. Okay, now, Jackson, Rena, you guys know the volume. Convince me you know the surface area of a cylinder. It's okay if you don't. So what is it, right? We want to minimize surface area. So area is equal to, what is the surface area of a cylinder? And so I'm going to take our cylinder and I'm going to fold up its top. I'm going to unwind its the siding, the wall there, and then unfold the bottom. Right. So here I just took the I took our cylinder and I kind of took it apart. Yes. Okay, Jax, you're right. I thought I would put you on the spot. Yeah. Okay. So here's how we figure out the formula for the area, the surface area of a cylinder. If we didn't have it, if we didn't know it already, you just take our object and we can just break it up into each of its sides. We have two circles with radius r, and we have a rectangle whose height is h and whose length is the circumference of the circle. And so now let's just find the areas of each of these shapes. The area of this circle is the same as the area of this circle, which is 2 times pi r squared, plus the area of the rectangle, which is 2 pi r times h. Okay, so we have this constraint equation that pi r squared h is equal to 1,000, and we want to minimize 2 pi r squared plus 2 pi r h. Again, this is a function of two variables, r and h, and we don't know how to maximize those. So what do we do to turn this into a function of one variable? So this is a function of two variables, r and h. We want to eliminate a variable somehow. How do we do that? Yeah, we could solve for, well, I'm not going to solve for r. I'm going to solve for h. We solve for one of the variables in our constraint equation. Whatever one will make it cleaner, will make our math cleaner, right? If we solve for r, we'd have a square root of 1,000 as part of our work. We'd have a square root of h. It would just kind of become a mess when we plug it back into here. So let's solve for h, but I mean, either way will lead us to the right answer. If we solve for h, we have h is equal to 1,000 over pi r squared. And really what we want to, now we could restate our question, and it says maximize or minimize a equals 2 pi r squared plus 2 pi r times 1,000 over pi r squared. So really what we're trying to minimize is the function 2 pi r squared plus 2,000 r to the negative 1. How do we minimize this? So we have this function, a is a function of r. How do we find the minimum value? Yes, find the derivative and find the critical numbers. So a prime is equal to, well, the derivative here, we'll just do the power rule twice. 4 pi r minus 2,000 over r squared. And in order to find the zeros or the critical numbers, it's best to put it all into one fraction. So let's get a common denominator, and we get 4 pi r to the third minus 2,000 over r squared. All right, now we want to set it equal to 0 or find when it's undefined. So when it's equal to 0, that tells us that the numerator is equal to 0. And when we solve for r, we get r is equal to the cubed root of 500 over pi. We should also check when the derivative does not exist. Right, if you don't believe me, just work out the math here. Add over the 2,000 and divide by 4 and then divide by pi, take the cubed root. A prime doesn't exist implies that the denominator is equal to 0, or that r equals 0. But we could throw out this case, because, I mean, for a number of reasons. One, that's not in the domain of our function. We'd be dividing by 0. But also, it doesn't make sense. You can't have 1 liter contained in a cylinder that has no radius. It would just be like a really long line. So this does not make any sense. Okay, so we have r is equal to the cubed root of 500 over pi. How do we get h? Everyone is a math expert. Oh, thanks. Using TI calculator. Okay, I'm not sure. I'm not sure how that's relevant, but okay, how do we get h? Yeah, we plug into our constraint equation. So h is equal to 1,000 over pi times the cubed root of 500 over pi squared. And this is a fine way to leave your answer. Okay, so I mean, you could simplify this. I think I simplify it in the notes. If you wanted to just practice your algebra. This actually simplifies to 2 times the cubed root of 500 over pi. But this answer here, so r is equal to 3, the cubed root of 500 over pi, and h is equal to this mess, that's a perfectly fine answer. All right, let's do one last example. This type of problem is a favorite of mine. So I don't know if you could put 2 and 2 together, but you may see a question similar to this again in the future. Test, quiz, or final somewhere. YouTube. So find the point on the curve y squared equals 2x. Okay, so this is like a parabola that's, I'll sketch it out in a second. That is closest to the point 1, 4. That it's scary math. Oh, no, this is not scary math. This is just applications. Okay, we want to find the point on this curve. And now it's, if you don't know what this looks like, that's perfectly fine. That's not important to the question, but just to kind of have a sense of what this looks like, y squared equals 2x is just the reflection of y equals x squared over 2. So it would be just a parabola going this way. And we want to find, and like 1, 4 is this point up here. We want to find the point on the curve. So it's going to be somewhere in this region that's closest to our point. All right, so that's kind of the idea here. So we want to minimize right, closest is another way of saying minimize. So we want to minimize the distance to the point 1, 4. Okay, so my question to you, how far away is the point xy? So just some random point in space, or in the plane. How far is that point from 1, 4? How far away is the point xy from 1, 4? So you don't have to type out the exact formula, but what is the name? Like, what do we use to figure out this distance? Yeah, we use the distance formula. Okay, so the distance that xy is from 1, 4 is the square root of x minus 1 squared plus y minus 4 squared. So we want to minimize this function, but it turns out it's easier instead we could minimize distance squared. Okay, we'll just minimize the inside of the square root, and that's going to be the same thing as minimizing the inside of the square root as long with the square root as well. So instead, we can minimize distance squared. Okay, so we really want to minimize sure, you could go along and just do it with the square root. It's just going to be a mess. So let's just minimize the inside. Right, and the reason why we're allowed to do this is if the the square root of a is less than the square root of b, then that tells us that a is less than b. So it's properties of the square root that allow us to do this, but you could learn about those properties in a later class. So we want to minimize the function x minus 1 squared plus y minus 4 squared. What's our constraint? So our constraint is that our point has to lie on this curve. Okay, so we want to minimize this function with the following constraint. We could solve for one of the variables. Again, it's probably easiest to solve for x, so we don't have to take a square root. And now we have a function that we want to minimize. Okay, so it's a function just of y, but just treat it like any other variable. And we want to minimize it. So we'll take its derivative. So bring the power in front, drop the power by 1, multiply by the derivative of the inside. Right? The chain rule still holds. Same thing here. Okay, and we want to take this and we'll set it equal to 0. So this becomes y to the third minus 2y plus 2y minus 8 equals 0. How did we get rid of the square root again? So instead of having, so we could just deal with the square root, and that's fine. But the square root has this property that if, so for instance, like this, if you know that the square root of 5 is less than the square root of 10, and that also tells us that 5 is less than 10. It has this property where if we had square root of a is less than square root of b, that implies that a is less than b. Okay, so if we want to minimize the square root, it's the same thing as just minimizing the inside of the square root. Okay, and so we got y equals 2. And now how do we get, we want to find the point. So how do we get, how do we get x from here? Yeah, so we'll, again, just like all the questions, we'll plug y equals 2 into our constraint equation to get x. So we have 4 is equal to 2x. X is also equal to 2. So the point 2, 2 is the closest point on our curve to this point. Based on our drawing, that seemed pretty believable, right? So I think that's a good place to stop. So for Tuesday, you have WebAssign homework on the curve sketching stuff, 3.5 and 3.6. I know we didn't technically cover 3.6, but it's just curve sketching with a calculator. So just use Desmos or whatever your favorite graphing calculator of choice is. Yeah, I'll stay around for a few minutes to answer questions, but we're going to do another full class of this optimization. So this is just kind of a start, but we'll see more of this on Tuesday. So does anybody have any questions or anything they want to share before I sign out? I'll be here for a couple more minutes. Remember, it's important. Got to hit the like button before you leave. It helps out the channel. Got to get to 1,000 subscribers. We're all committed to this. But if you don't have questions and you're leaving, just be safe this weekend. Practice the social distancing. It's we're on the home. I don't know if that's true, but we'll get through this. Be patient. Think of your parents, right? Sure, you may be fine, but those old timers, they're the ones we got to be thinking of. So just stay in your basement, play your video games, play some Minecraft. That's a great game. Fortnite, sure. Just stay inside. I don't know. That wasn't a very good speech, but all right. Bye-bye.